So in this video, we're going to graph secant x and cosecant x. So first we're going to start with cosecant x. And to do this, just a reminder of what cosecant x is. Cosecant x is the reciprocal of sine. So cosecant x is 1 over sine x. So to graph cosecant x, we're going to use sine x. And basically I'm going to recreate that sine x graph, and from the graph of sine we're going to get our new graph. So just making a table of values. When the angle is 0, sine is 0, and I'm going to write it as 0 over 1 to help us find the reciprocals. When the angle is pi over 2, sine is 1, and again I'm going to write it as 1 over 1. You'll see why in a sec. When the angle is pi over 4, sine of pi over 4 is root 2 over 2, which is approximately 0.71. So continuing with a few more angles in our table here. We can also do negative pi over 4. Sine of negative pi over 4 is negative root 2 over 2. So that's negative 0.71. If the angle was negative pi over 2, the sine of negative pi over 2 is negative 1, or negative 1 over 1. And the last one I'm going to do is negative pi. The sine of negative pi is 0, and I'm going to write that as 0 over 1. So I made all these fractions on purpose. I wrote 0 as 0 over 1 on purpose to help us with the reciprocal in a moment here. But for now I'm just going to fill in these points. So all the points from our table I'm going to fill in. And not going to be surprised, right? We've graphed sine of x numerous times on our previous assignments, so no surprise what this sine x graph looks like. Kind of starts in the middle there at 0, 0, and it makes this sine wave. Period is 2 pi, because that's how long it takes to make one full wave. Okay, so now let's get these cosecant values. So if cosecant is the reciprocal of sine, I'm going to take all these sine fractions and flip them. So the cosecant of 0 is 1 over 0, which we know is undefined. If you have 0 in your denominator, that value is undefined. Continuing with my other values, 1 over 1, well, the reciprocal is still 1. For our pi over 4 angle, it's 2 over root 2, which is approximately 1.41. So same thing with cosecant of negative pi over 4, that's going to be negative 2 over root 2, which is negative 1.41. When the angle is negative pi over 2, it's negative 1. And when the angle is negative pi, another undefined, right? We'll have 1 over 0 or undefined. So let's plot these points now. And I'm going to do this in red pen. So at pi over 2, the point is still 1. At pi over 4, the point is now 1.41. At negative pi over 4, it's negative 1.41. And at negative pi over 2, it's negative 1. So what about these undefined? Well, if the value is undefined, that's not the same as 0. Undefined means there's no point there. There's no value at that x value. So when x is pi, cosecant is undefined, and we're going to show that with a vertical asymptote. Same thing at 0 degrees or 0 radians. Same thing at negative pi radians. Those values were undefined. So what's happening here with our graph? These humps are kind of reflected outwards. The graphs in red here are not going to touch those dotted lines because cosecant is undefined at those dotted lines. So here in red is the graph y equals cosecant x. Those red graphs won't touch those dotted lines. Okay, let's do same kind of process with secant x. Well, as a reminder, secant x is the reciprocal of cosine. So secant x is 1 over cosine. So I'm going to start by drawing the cosine graph. And I won't go through the whole table of values. By now, hopefully we know what the cosine x graph looks like. The point 0, 1 is on that graph. Kind of at the top of my my first hump there. So think about where these vertical asymptotes exist. They exist when the sine and cosine graphs equal 0. So let's look back to our cosine graph. When does it equal 0? When the cosine graph equals 0, that's when you're going to have a vertical asymptote for secant. So here I'm adding my vertical asymptotes when cosine is 0. That's going to kind of give me kind of these boundaries. So now all I got to do is just kind of reflect these humps outwards. And that's going to be your graph for secant x. These red graphs are secant x. And again, they're not going to touch those asymptotes. They're going to approach them and get very, very close to them, but they're not going to touch them. And they're going to go infinitely upwards and infinitely downwards. So I'm always encouraging you to use desmos.com as a way to check your work and gain further understanding of what these graphs look like. So I've started you off with sine and cosecant. So there's the sine graph in red there, and in blue is the cosecant graph. They're going to go upwards infinitely and downwards infinitely. And as they, continue infinitely up and down, they get closer and closer to those vertical asymptotes. What we call infinitesimally close to those vertical asymptotes. And if I zoom out, you see, it continues in a pattern, infinitely left and right too. So there's this infinite pattern that's going to exist. You can check out the other one we just did, secant. So here on my tablet I have cosine x and secant x. So in red there is the cosine graph, and in blue is the secant graph. So a similar kind of look, right? In fact, they do look very, very similar. Hopefully by now you've picked up that, the sine graph and the cosine graph are basically the same, except for a phase shift left or right. So let's do an example here. Find the period and graph the following. Y equals 3 secant 2x. So one thing you got to know, secant and cosecant don't really have amplitudes. We talked about amplitudes for sine and cosine. Not really correct to say that secant and cosecant have amplitudes. So we're not going to pay too much attention to that. But they do have periods. And we're going to look to that k value again to get that period. I guess what you would call standard form for secant, it looks like the cosine graph, the cosine equation. So to get that period, we're going to again do 2 pi over k. K in our example is 2, so 2 pi over 2 is pi. So that is my period. That's how long it takes to make one full wave. Not just for cosine, but for secant as well. Based on my equation, my example, there really is no phase shift. It's just x in the parentheses. So we're not going to do any kind of shift left or right. So let's try to graph this. And what I'm going to do is I'm going to graph as if it were cosine first. So let's graph this as if it were cosine and not secant. So setting myself up with some axes here. I'm going to go from negative 2 pi to 2 pi on my x. I'm going to go from negative 3 to 3 on my y. So again, we got the period to be pi. So it takes a distance of pi to make one full graph. So let's graph it as if it were cosine with a period of pi. So I know that cosine, the hump kind of starts in the middle there. So that's why I started my hump in the middle there. And basically I just made it so that I completed one full wave in a distance of pi. I basically got back to my starting point after pi units. And I'm just showing you again what I mean by that middle hump. That middle hump for cosine exists on the y-axis before any kind of phase shift. So each time I have another pi on the x-axis, I make another full wave. Start to finish, it takes 1 pi distance. Start to finish takes 1 pi distance. Alright, so this is what it would look like if it were 3 cosine 2x. So, if I'm going to make it secant, I'm going to want to be aware of these asymptotes. The asymptotes occur when cosine is 0. And once I kind of have those asymptotes in place, I can reflect out these humps. So it's kind of hard to see the period with this red graph, with this secant graph, because it's not really a wave. But the period would be basically pairs of these outward red graphs. So each pair would make up one complete cycle of the graph. And that exists in a span of 1 pi. All right, let's do another one. If the graph is y equals cosecant pi over 2 parentheses x minus 1. Let's get that period first. Well, k is pi over 2. This is a little bit different. Our k value has a pi in it. So I'm going to put it under 2 pi. 2 pi over pi over 2. We have to reduce, just like dividing fractions. We'll multiply by the reciprocal. So when all is said and done, my period is 4. So this is a little bit unique. My period doesn't have a pi in it. The period is just 4. My k value had a pi in it, but my period doesn't. So that's going to affect how I set up my axes. Knowing that my period is basically a counting number, like 4, I'm not going to put pi on my x-axis. I'm going to put counting numbers on my x-axis. That's just looking ahead to what my period is. So I'm going to count by ones. I'm going to go from -4 to 4 on my x-axis. I'm going to go from -1 to 1 on my y. I'm going to graph it as if it were sine. So I'm going to graph first in black here as if it was sine and not cosecant. Well, my sine graph starts at 0, 0. If there is no phase shift, sine starts at 0, 0. And basically I'm just going to make it so that one complete wave happens in 4 units. Same thing on the left side here. My period is 4, so one full wave in 4 units. So here in black is if it was sine pi over 2x. So actually I haven't implemented the phase shift yet. In black I've just graphed sine pi over 2x. So I'm going to kind of do this in baby steps. Almost kind of 3 parts here. So now I'm going to implement the phase shift. The phase shift is 1 unit to the right. And you'll notice that that phase shift of 1 unit kind of agrees with the fact that we're counting numbers on the x-axis. So I'm going to move 1 unit right. So that graph's going to go in blue here. Basically, the entire block graph gets shifted 1 unit right. So in blue here, we have y equals sine pi over 2 x minus 1. So it's this blue graph that I'm going to use to create my cosecant graph. So, like before, I want to identify those asymptotes. When is cosecant going to be undefined? When sine is 0. So that's where those vertical asymptotes are going to exist, when sine, that the blue sine graph is 0. So now to finish it off, I'm just going to reflect outwards. And that kind of finishes up my graph. So in red here, I have my final answer graph. That is y equals cosecant pi over 2 x minus 1. Kind of a mess of stuff there. Obviously, if you were doing your homework or whatever in pencil, you could erase all that mess inside and leave just your red graph. But that's how we do it. So I'm going to, once again, go back to my tool Desmos. And on my tablet here, I've graphed basically the three graphs we just showed. So in red, I have sine of pi over 2x. And if you notice, on the graph, sure enough, that period is 4. One full wave over a distance of 4 units. So my period is definitely 4. In blue, I've added in the phase shift, 1 unit right. And then finally in green, I made it into cosecant. So I have these I guess humps that, reflect outwards. So that definitely agrees with the graph I put on paper. So we feel pretty good about what we did on paper. The graph in Desmos agrees. And that's all there is to it.